In computer science, basically three different numbering systems are used: decimal, binary, and hexadecimal. So in order to be successful in computer science, you'll need to understand how these numbering systems work and how to convert from one numbering system to another. I have put together a little video for you that you can take a look at by clicking on this link here, which shows you the Windows Scientific Calculator and how you can use it to convert values from one numbering system to any of the other numbering systems that we'll be talking about. So let's look at these three numbering systems now in a little bit greater depth. We'll start with the one that you're most familiar with, which is the decimal system, or base 10. It's called base 10 because it's based on multiples of the number 10. And the entire numeric system only has 10 digits, 0 through 9. When we write out a number like 246, what we're really doing is we're organizing these numbers into columns, and each column is assigned a value of a multiple of 10. Those multiples of 10 are the powers of 10. We start with 10 to the 0 power in the right-hand column. We continue into the second column with 10 to the first power, and that's followed by 10 to the second power, and if we continued on, we'd have 10 to the third power, 10 to the fourth, etc., etc. And if we translate the powers of 10 then into their individual values, you'll see the actual numeric values of each column. So 10 to the 0 power is the ones column, 10 to the first power is the tens column, and 10 squared is the 100ths column. So the number 246 really means to take the number 2 and multiply it by 100, add to that 4 times 10, and 6 times 1. Add up those three numbers, and that's how we get the total, 246. So now let's apply these same principles to our other two numbering systems. Let's move on to the binary system, or base 2. It's called base 2 because it's based on multiples of the number 2, and there are only 2 digits in that numeric system. This is a representation of a binary number, 1010, and again it's being organized into columns. This time the columns are represented by the powers of the number 2. So we have 2 to the 0 power, 2 to the first, 2 squared, 2 cubed in this example. The numeric values of each of those then represent the value of the column, and so the first column is the ones column, the second column is the twos column, the third column is the fours column, and then the fourth column is the eights column. So in this example what we're saying is we would like to multiply 1 times 8, add to it 0 times 4, add to that 1 times 2, and add to that 0 times 1 for a total of 10. So the binary value 1010 is the same as the decimal value of 10. Let's now take a look at the hexadecimal system, again applying these same principles. Hexadecimal is base 16, which means that it's based on multiples of the number 16, and there are 16 digits in this numeric system. You'll see that once we get beyond 9, we start using letters. So A represents decimal 10, B would be 11, C would be 12, D would be 13, E 14, and F is the equivalent of decimal 15. Let's write out a number here in hexadecimal. So 2E6 is an example of a 3-digit hexadecimal value, again organized into columns, and each of those columns represents a power of the number 16. So we have 16 to the 0, 16 to the first, and 16 squared, and then the numeric representation of each of those powers again is the value of the column. So we have the ones column, the 16s column, and the 256s column. So let's translate that just like we did previously. The first column, or I should say the third column, is 2 times 256. We'll add to that 14, because remember E is the equivalent of decimal 14, and it's in the 16s column, so we multiply 14 times 16, and then in our last column 6 times 1. So we add up the total of those three values and we come up with our final result of 1,414. So 2e6 in hexadecimal is the equivalent of 1,414 in decimal. When you're working in a field that involves computer sciences like programming, networking, or information technology, it's important that you are capable of being able to convert numbering systems. So take a value in one numbering system and convert it to the comparable value in another numbering system. So what I'm going to be demonstrating to you in this tutorial is how to convert a decimal number into a binary number. We do this by using this table that you see here on the screen. It's an 8-column table that also has 3 rows. And in the first row, we're going to place the powers of 2. So I'm going to start in the far right-hand column there, column number 8. And I'm going to just put in 2 to the 0 power. Then I'll move over to the next column, put in 2 to the first power. Then 2 to the second power. 2 to the third power. 2 to the fourth power, 2 to the fifth, 2 to the sixth, and then 2 to the seventh power. So this table is going to represent 8 bits or an octet of an IP address or a subnet mask. Remember, an octet is a grouping of 8 bits. And so we've put in, starting with 2 to the 0, then each of the powers of 2 all the way up to 2 to the 7th power. So that's our first row, the powers of 2. The second row then is the decimal value row, and in this row what we do is we put in the conversion of each of the powers of 2 into its decimal equivalent. So 2 to the 0 power is 1 in decimal, 2 to the first power is 2 in decimal, 2 squared is 4, 2 to the third power 8, 2 to the fourth power is 16, 2 to the fifth 32, 2 to the sixth 64, and 2 to the 7th, 128. So those are each of the decimal values, the decimal representations of each of those powers of 2. If you didn't know the powers of 2, it's really not difficult. If you look at how this works, the decimal row starting on the far right-hand column, column number 8, as long as you can remember that that is the value 1, 2 to the 0 power is the number 1, then as you move to the left, you just simply double that number each time. So 2 is twice as much as 1, 4 twice as much as 2, 8 twice as much as 4, etc., etc. So that's basically the table that you need to set up to be able to make this conversion from decimal to binary. Now, the decimal number that I'm going to select for our demonstration here is the number 255. This is a number that's commonly found in subnet addresses, so I think it's a good idea for you to see what that looks like in its binary version. And we're going to put the binary version, or the binary information, the ones and the zeros, into the last row. So you can see that row is labeled binary digits or bits, and we'll place either a 1 or a 0 in each column, which will identify whether or not we're able to use a particular decimal value, the value above it in each column. When you are doing the conversion process, you want to work from the left to the right as you analyze each of the decimal values. For instance, we've got our starting number, the number that we want to convert, 255, and I want to look at the decimal row and go from left to right, highest to lowest, and see what is the first value there that I can subtract from my current number. So when we look at 128, that is less than 255, so obviously we can subtract that from 255. Now, to indicate that I can subtract 128 from 255, then I put a digit, a value of 1, into the column underneath of 128. So that's the binary representation that says that I am able to take or subtract 128 from 255. Then I do the math. I subtract that 128 from 255, come up with the remainder of 127. Now I'll repeat that process for each of the times that we end up with a remainder until we get to a remainder of 0. So now my current value is 127. I want to look again at the decimal value row and see what is the highest number, working from left to right, that I can use and be able to subtract from 127. Of course, that number is the number 64. So I place my 127 at the top. I identify 64 as the value I can subtract from it. I place a bit underneath of that value in the binary digits row, and then I go ahead and again perform the math, subtract 64 from 127, and I come up with a result, or a remainder, of 63. Just keep on repeating that process now. We've got a remainder still, 63, so we want to identify what can I subtract from 63. So we'll start with 63. We'll identify that 32 now is the highest value in the decimal row that I can subtract from 63. So I put a 1 into the binary digits row, I do the math, subtract 32 from 63, and we have a remainder now of 31. Again, I'll take that remainder, 31. I'll look and see which is the highest value I can subtract from it. It's 16. I'll go ahead and put a 1 in the binary digits row, and then do the math, subtract 16 from 31, and I get a remainder of 15. Take that remainder, 15, identify which is the next value I can subtract from it, and of course that's 8. We'll put a bit then in the 8 column in the binary digits row, and then do the math, subtract 8 from 15, and end up with a remainder of 7. So what can we subtract from 7? The highest number in the decimal row would be 4. We'll indicate that we're using 4 by putting a 1 in the column underneath of 4. Then do the math, subtract 4 from 7, get our remainder of 3. Take that remainder, figure out which value in the decimal row I can subtract from it. Of course that's 2. We'll indicate we're using the 2 with a 1 bit in the binary digits row under the column of 2, and then finish off the mathematical process here of 2 being subtracted from 3 and receiving a remainder of 1. We take that remainder of 1, again, we can see that 1 now is the value that we can subtract from it. And no other values in that decimal row could be subtracted from 1. So we'll go ahead and put a bit, turn on the bit there, put in a 1 for the binary digit to represent that we're using the decimal value 1, and go ahead and subtract it from our 1. Now we come up with a remainder of 0, so now we have completed the process. When you look now at that binary digit row, you'll see it is a sequence of contiguous 1s there. It's 8 1s, and that is the binary representation of the decimal value 255. So every time you have a 255 that you see in a subnet mask, the way the computer sees that is a contiguous collection of 8 1s. So I want to make sure you're getting the hang of this here, so let's go through this decimal to binary conversion one more time. This time we're going to use the number 236 as the decimal value that we're going to convert to binary. And we'll look at our first column in the decimal values here, and we'll see that 128 is a number that we can subtract from 236, so we'll go ahead and put a 1 there in the binary digit row to indicate we can subtract 128, and then go ahead and do the math. Subtract 128 from 236, and we get a remainder of 108. So that's the number now that we need to subtract from. Our remainder of 108, and we look to the next highest value, which is 64, and see if we can subtract that from 108, and of course we can. So we'll go ahead and add a bit into the binary digits row, and then again do the math, subtract 64 from 108. Now we take our newest remainder, the 44, and again we look for the highest value that we can subtract from it. That is the number 32. We'll go ahead and indicate that we can subtract 32 from our 44, again by putting a 1 in the binary digit row, and then we perform the math, subtract 32 from 44. Our remainder now is 12, so we look for the next highest value that we can subtract from 12, and 16 is not a number in this case that we can subtract from 12 and still have a positive value or 0 or greater as a result. So we're going to put a 0 then in the binary digits row to indicate that 16 cannot be subtracted from the remainder. So we'll move over now to the next column, to the 8 And of course that is a number that we can subtract from 12 and still end up with either 0 or a greater value in the remainder. So we will put a 1 in the binary digits row to indicate we will be using an 8, subtract it from the 12, and we get a remainder of 4. Now we look at putting the remainder up and identifying which value from the decimal value row that we can subtract from it. And that number, of course, is the number 4. So we'll put a 1 into the binary digits row to indicate we can subtract number 4 from 4, do the math, and now we come up with a 0 remainder. So at any time you hit a 0 as your remainder, then you're done as far as the conversion process is concerned. And so that means all of the remaining columns, like the 2 decimal value, can't be subtracted from 0, so we put a 0 in the binary digits. And then the 1 also can't be subtracted from 0 and still have 0 or greater as the remainder. So we just finish out the remaining bits with zeros as soon as we reach that initial remainder value of a 0 while calculating our decimal to binary conversion. So when we take a look then at our results, we can see that the binary value of 11101100 is the equivalent then to decimal 236.